we're talking about a string that lives in a space-time of 26 dimensions. And therefore, when I say we're going to make an orbifold R1 divided by Z2, that means that you pick one of those 25 spatial dimensions, and you decide, okay, in that dimension, I'm going to consider a line only. And all the other dimensions are perfectly non-compact the way they used to be. So we have the x plus, the x minus, and then the transverse coordinates that used to be called xi, now split into xi's, little i's, and x25, which is the last coordinate that conventionally we call it just x. And we define an orbifold by trying to construct an operator u that would take x of tau and sigma and give you minus x of tau and sigma. This operator, as we discussed last time, has a property that does all kinds of things to the operators that we're familiar with. So, for example, on x0, on p, on alpha n, on alpha bar n, all these signs are reversed. But for example, if you would have an alpha I n, that sign would not be reversed. So you get here a minus x0, minus p, minus alpha n bar, and here you would get alpha in. If it's a non-orbifolded coordinate, this is perfectly okay. So we're trying to figure out now the spectrum of this thing. So how does it go? Well, you could say, all right, I had ground states before. What were they? P plus, P transverse. Okay, that seems reasonable. Let's think of ground states. I'll be more explicit, in which I have P plus, Pi, and P. Because all the transverse coordinates have an I for all the many ones that have been left untouched, and the last one, the 25. So on the other hand, the operator P associated to that last eigenvalue is a reverse sign under the orbifold operation. So we can say that the U operator on P plus Pi P is equal to P plus Pi minus P. And you would say, okay, so what are my ground states? They should be left invariant under the orbifold action. So my real ground states, you would say, should be true ground states. Because at this moment, we have to pick up only the states that are invariant under the action of the operator U. So true ground states are perhaps these ones that I would call P plus states, which are P plus Pi P plus P plus Pi minus P. Our usual trick that if a single state, you could say, oh, the only ground states are the states of zero momentum because they're unchanged. Zero momentum in the orbifold direction, but that's not true. You could make a state like this. The action of U gives you this. The action of U on this one gives you that. And this state is invariant. So we'll go there. And then let's look at massless states. Now, why these are still tachyonic states. The mass squared operator still is 2 over alpha prime n plus n bar minus 2. And this counts the numbers of the oscillators in all directions, the x25th included. So this remains a tachyonic state. And let's look at massless states. Okay, massless states, I could do the following. I could put a state of the form this: alpha minus 1 I, alpha minus 1 bar j. Look what I've done. There's equal number of minus 1 here for a right-moving oscillator, minus 1 for a left-moving oscillator. So this will satisfy that n perp is equal to n bar perp. So that's fine. If I put now the ground state P plus here, that seems to be orbifold invariant because the alpha ni's are not touched, or the alpha bar ni's, this also includes the alpha bar in's, are not touched by the u action. We said that the u action on the xi's was plus xi's. Doesn't do anything to them. So this is a good state. There is another good state that you could put here, alpha minus 1 bar p plus, because the action of the u operator reverses the sign of an alpha that doesn't have an index, that's an alpha 25, and reverses the sign of the alpha bar. So two reversals of signs in the P plus, that's still a good state. And if you're not terribly careful, that would be the end of the story, because you would say, okay, you suppose you do this, alpha minus 1, alpha minus 1 bar I. Well, it's an I oscillator that's not, doesn't change sign under U, but this one does, so this state would change sign. So that doesn't look good. On the other hand, you could say, oh, that can change sign, but how about if I invent another one here, a P minus, a ground state P minus that is not part of the theory, so I haven't boxed it, but I define it. PIP minus P plus PI minus P. That ground state, that is not a ground state of the theory because not invariant under the orbifold projection, when you act with U, it reverses sign. So actually, on these combinations of oscillators that reverse sign, if I put the P minus state, I get a good state. Because there's one change of sign for this and one change of sign for that. So then I can also have alpha minus 1 I, alpha bar minus 1, P minus. And these are all massless states. From the viewpoint of the lower dimensional field theory, suppose you live in a world and you try to ignore the 25th coordinate, these states contain the graviton, the antisymmetric tensor, and the Kalb-Ramond. These are scalars in the lower dimensional world because they have a 25th index that you're ignoring as if it would be a compact dimension. This would look like vectors, a gauge field and another gauge field. At any rate, that's it for these states. And we would say, all right, so we're done with the orbifold. But the orbifold is not done. The most interesting part of the orbifold comes now. When you do an orbifold in string theory, there's two things that happen. You have the parent theory. And that parent theory that we've discussed loses some states because you keep only the states that are invariant under the U action. But in the orbifold theory, there appear new states. You can quantize the string in a different way in the orbifold theory. There's called the twisted states of the orbifold, and we're going to discuss them now. They're very non-trivial. So this is not the end of the spectrum of the theory. So we're going to call, we say, twisted states. So when we quantize the theory, we put a boundary condition that we said the closed string must close. And you say now, oh, the closed string must close maybe allows us to do something different. It would allow me to, here is the x coordinate that is being compactified, x25, which is equal to x. You know, here's another coordinate, maybe a y coordinate. Suppose I have a closed string. A closed string could be closed, but the closed string could just begin here, do some funny things, and end up here, where this is, say, a point B, and this is minus B, because this point is the same if it's at the same height. This point is the same as this one, because of the orbifold identification. So the string may look open, but it's really closed. So we said x25 of tau sigma plus 2 pi. We used to say that it had to be equal to x of tau sigma plus 2 pi, and that's indeed true, and we got all the states that satisfy this boundary condition. But now, this is an equally good closed string. If after you've gone from sigma equals 0 to sigma equals 2 pi, you end up in a point that is minus the original one, well, since we've identified these 2 points, you are closed. So we need to analyze what does this give, and this gives you an x that is periodic with period 4 pi. It's periodic, period 4 pi. But another thing that is sort of interesting is that there is some sigma, exists some sigma star, such that x of tau sigma star is equal to 0. This closed string takes points, takes values, and takes the negative values because it closes by ending at the negative point where it started. So if it takes positive values and negative values of x25, there must be sigmas for which it takes the value 0. So these strings are intuitively, they're stuck at the orbifold point. They always have to pass by the point x equals 0. And you know, the longer, they can be very long, but that's very expensive in energy. This costs tension. So all these strings really like to be near the point x equals 0. They sort of live at the fixed point of the orbifold. They don't quite, because they oscillate around it, but you know, they're sort of stuck. You give a string a finite amount of energy, and you can't find that string far away. Let this be the fixed point. You can't find it here, because that string would have to then go all the way to the -1 to close. It would be an extremely long string. So that's the main intuition of the twisted sector. It's a new set of closed string excitations that will end up living at this point. So we'll see how the mathematics confirms this intuition. So we do as before. We say x equals x left of tau plus sigma plus x right of tau minus sigma. So far, so good. It must satisfy the wave equation. But when I substitute here, what do I get? I get x left of tau plus sigma, which I think we called u, and this we called v. So x left of u plus 2 pi plus x right of v minus 2 pi is equal to minus, this time, the original one. So minus x left of u minus x right of v. As before, we put all the things with u on one side and all the things with v on the other side. So we have x left of u plus 2 pi plus x left of u. This before we had the failure of periodicity. This is sort of crazy. It's the sum of these two things. On the other side, we have minus x right of v plus x right of v minus 2 pi. Well, still, we used to say that the u and v are independent variables, so if those two things are equal, this must be a number, and that must be a number, and they must be one negative of each other. And what do we see here? If we take a derivative with respect to u, we used to say that xl, with a minus sign, you take a derivative with respect to u, so you get x prime left u plus 2 pi plus x left prime of u is now 0. So actually, this coordinate is anti-periodic. It's funny because this is going to reappear very soon in the superstring with the Navier-Schwarz sector of the superstring. Things are beginning to be anti-periodic and all that. So whatever we're going to get today is not going to, it's going to be surprising, but we're going to see it again with the superstring. So this is so x left is anti-periodic. So x left of u plus 2 pi is minus x left of mu prime of u. And the same for v. Okay, so anti-periodic. So what can we do? Well, we have to write a mode expansion. So we do it. X left prime of u equals. Your experience with closed strings shows that you probably should put this, and you will sum over some sort of integers. Yes. Oh, yeah, I'm sorry, sigma. Yeah. It has to be one like that. Thank you. Ooh, sorry. Okay. So what do we do here? We need things. Well, what did we used to have? Don't copy this. We used to have alpha n e to the minus I n u, because this had to be periodic. But this is no good anymore because it's not periodic. When you change u plus 2 pi should be anti-periodic. But that means that you know, things are periodic with period 2 pi, but if you just change, when u goes from 0 to 2 pi, if you had a fraction in front, like 1/2, this would go e to the I pi, and it would change sign. So actually, you have to have things that are like 1/2, 3/2, 5/2 in here. So I'll put here n over 2. But n over 2, you know, what we really wanted is something like 1/2, 3/2. So n will sum over z odd. And that would be anti-periodic. If you put u plus 2 pi, u plus 2 pi with n odd is going to be anti-periodic. You're going to get a multiple, n multiple of pi, and with n odd, so it's going to reverse sign. And then there's another piece of notation here. This thing gives you the e to the minus I n tau plus sigma. And this I n tau is like in the Schrödinger equation, n was the energy of the oscillator in the number operator. So this n was n here, and everything worked out fine. All the conventions worked out fine. So actually, it's a good idea, instead of putting alpha n here, to put alpha n over 2 as a label. The same thing that is here, you put it here. Now, at this moment, it's just a matter of notation, but This is the issue, that you have this ones to some is not a matter of notation. Whether you call this alpha n or alpha n over 2, it's a matter of notation. But the physical expectation is that these are correlated if you want to keep the same formulas for the number operators. So for x prime right of v, we'll do the same thing. Now, I don't know. Oh, it's left, so bars. Alpha prime over 2, sum over n odd, alpha n over 2, e to the minus I n v over 2. Well, now, if I integrate this, I would have xl of u equals some little xl, because that drops out of the sigma derivative, plus oscillators. And many times you write this because you don't want to copy so much, that are anti-periodic. Because you would just integrate over u, and you get factors of 1 over n, but the same exponentials will remain, and it's anti-periodic, which is AP. And x right of v would be x right plus oscillators. But if we go back to our main equation, I substitute these expansions now into the main equation here. What do I get? For the left-hand side, I get this xl plus another xl from the u plus 2 pi and u. But the oscillator part cancels because it's anti-periodic. From the right, you get x right, 2 times x right, and the oscillator part cancels. So back in equation A, we get x left, 2x left is equal to minus 2x right, or x left plus little x left plus little x right. Maybe I should put a 0 there. I didn't put them. Is equal to 0. Those little x's. So when we add up the two of them, let's now continue. When we add up the two of them, x left, x of tau and sigma is going to be x left of u plus x right of u of v. And I must add these two, but you get x left plus x right are 0. So you don't get a 0 mode. And that's perfect. You get what? You get just the result of those integrals that we just didn't do, but take one line to do. Sum over n belonging to z odd 2 over n e to the minus I n tau over 2 alpha n bar e to the minus I n sigma over 2 plus alpha n over 2 e to the I n sigma over 2. So look, the expansion of, we're finished with the mode expansion. The expansion has no 0 mode for x and no momentum. There's no I alpha prime p tau in the expansion. So this states, as we would expect from the boundary condition, really don't have a 0 mode that they can move really freely or a momentum associated to them. A free string in a twisted state of the orbifold cannot have momentum in the orbifold direction because it would just start moving in that direction forever, and that is impossible. So no x nor p. No x or p. No x0 or p or little p. That's very nice. Now, if you take your expansions here and do the same thing we used to do before, calculate x dot plus x prime and x dot minus x prime, we get the same thing of usual. 2 alpha prime sum over n odd this time, alpha bar n over 2 e to the, all these things that 2 alpha prime sum alpha n over 2. The conventional stuff with the correct factors of everything. So when you now look at what the commutators are between the alphas, they must satisfy the same formulas as before, with the n's replaced by n over 2. So the commutators here are alpha m over 2 bar alpha n over 2 bar is equal to, we used to have alpha m, alpha n equal m. So here it's going to be m over 2 delta m plus n 0. Similar thing for the other ones, alpha bar, alpha m over 2, alpha n over 2. This is equal to the same thing, same. And the alphas of one type don't commute with the alphas of the other. It should be said that the orbifold projection still exists. So the U operator must still act on those twisted states. So we need that U on this nu x, U is minus x. So the alphas change sign. So the U on alpha n over 2 or alpha bar n over 2, U, if you minus alpha n over 2 or alpha bar n over 2. So the orbifold projection still exists, and when you build states with the alpha fractionals alphas, you still have to worry that you produce states that have the right invariance. They're U invariant states. The last hurdle here is the mass formula. Let me remind you of what happens here. So let me write the mass formula for closed strings is alpha prime m squared is equal to n plus n bar plus this 2a thing. In the old case, this formula, we've written it before already there. It's the same formula. In the old case, a was equal to minus 1 because it was equal to minus 124 times 24. I write it like that to remind you that each time you had to reorder the oscillators in L0 for one coordinate, you got a minus 124. And then there were 24 coordinates. And that came from the L0. Is that right? So the L0 operator, perp, is 1/2. You sum over all p's of alpha p little I, alpha little I minus p. Let me write this formula and then explain it. The sum over k belonging to the odds, alpha k over 2, alpha minus k over 2. What was L0 perp? L0 perp was sum alpha 1/2 alpha n I, alpha minus n I. You summed over all transverse directions. So this comes again, it will happen that the transverse directions now run over little i's and the x25. So since everything has been set the same way, L0 perp now runs here over not quite 24 of this, but just 23 of this. I runs from 1 to 23. And the last one, which was x25, gives you this. It's just completely analogous. You know, you have the oscillators of the 25th coordinate now. They are in this twisted sector, so these are the fractional oscillators. So how did we get this constant? For the left movers, you got an A. For the right movers, you got another A. So this L0 got an A because you had to reorder this once, and when you had the trace, or the sum over I, you had the factor of d minus 2. But now there's, of the 24 coordinates, 23 are normal, and 1 is twisted. So the total constant A that we're going to get, I want to finish pretty much in 5 minutes that thing. The total constant A that we're going to get is going to be 23 of those that you have minus 1/24 for 23 coordinates here, as you reorder, plus the extra from the twisted one. Twisted. Because we also have to reorder these guys. So let's look at those, that term. So that term is 1/2 sum over k odd, alpha k over 2, alpha minus k over 2. Now we can sum over the positive odds. The positive odds are, these ones would be creation operators. This would be annihilation operator. So it's probably a little, those are going to be the ones that we have to rearrange. And then we have the ones that are the negative odds. The negative odds are well ordered because these modes would be positive. So these are destruction. These are creation. So at the end of the day, we get what? We get the sum over k odd belonging to positive odds. And we get 2 of those because the positive and the negative give the same after reordering. And in the reordered version would be minus k over 2, k over 2. So the negative ones and the positive ones are combined. There's no 0, 1 because we're doing at odds. And then the ones that we have to order here are plus 1/2 the k odd and positive. Those are the ones that are badly ordered. So for them, to get them to contribute to this, you have to do the alpha k commutator, alpha k over 2, alpha minus k over 2. So this thing is the constant that we're going to get. And how much is this constant? This is equal to 1/2 the sum over k odds of k over 2. So it's 1/4 of the sum of 1 plus 3 plus 5 plus 7 plus. Now the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus is minus 1/12. We all agree of that. And then, if I do the following, this is 1 plus 3 plus 5 plus, take the odd ones, plus those, plus 2 plus 4 plus 6 plus 8 plus, which is the sum over k belonging to z odd and positive, plus twice the sum of all integers, which is minus 1/12, is equal to be minus 1/12. So the sum of all odds sum of 1 plus 3 plus 5 plus that is equal to plus 112. So this is plus 112, and this is therefore 148. So for an antiperiodic coordinate to reorder things costs you not minus 124, but costs you 148. So actually, extra from the twisted equals 148. And this result gives you minus 15 sixteenths, the total A, or minus 15 sixteenths. So the mass squared formula is 1/2 alpha prime m squared equal n plus n perp minus 15 eighths, 2a in there. So it's a funny thing. We really have to use this heuristic way of doing sums, but it's reliable, and that's the famous answer for the normal ordering constant of orbifold. It's pretty important. That number decides whether you got a tachyon, a massless state. You're not going to get massless states from the twisted sector because these number contributions are fractional, can be fractional from the orbifold direction, but factors of 1/2. So let's write a couple of states here. Ground states. Well, you started with P plus Pi and P in the orbifold direction, but there's no P in this orbifold, no P0 modes. The states are really stuck at the orbifold plane. I call it a plane because it's a point in the 25th direction, but that point has all the other coordinates accompanying it. So we should forget about this. It's some sort of ground states that don't involve this momentum. Now, what are the excited states? The lowest excited states that you could construct. You have to watch out for many things now. You have to watch out that n is equal to n bar from left and right. You have to watch out that the state is U invariant. And that's it, pretty much. So what is the lowest thing? The lowest thing, you could use the oscillators of least weight, and those are the oscillators in the orbifold direction. So you could put an alpha minus 1/2, which is a creation operator. But if you put an alpha minus 1/2, you would have to put an alpha bar minus 1/2 for n equal n bar for closed strings. And here is P plus Pi. That's the lowest excited states. And how much is the mass squared from here? 1/2 alpha prime m squared would be the value of n, which is 1/2, the value of n bar, which is another 1/2 contribution from here, and the minus 15 eighths. So it's minus 7 eighths here. It's still a tachyon. And then you can build more states, and you can count the states, and you can do all kinds of things with them. And they all live, they're excitations that live at the orbifold fixed point. So that's it for the orbifold. Yes? Well, I'm not sure. Yeah. Well, you know, it's not like we first compactify and then quantize. The first sector that we did was called the untwisted sector. Is the original sector. We took the original expansion and then said, okay, let's compactify. And the action of compactification in our case is just the action of stating that the states are invariant under some symmetry. So that's what we mean by being compactified. Now, in the second case, however, we're doing sort of the opposite thing. We use very non-trivially the fact that the space is compact, not compact really, but has been tinkered with, and we took the expansion of the string and used that to requantize the theory and resolve everything. So in the second case, we did a little more of what you would say is the obvious thing to do, is to see what is the new space and do the quantization. But at the end of the day, basically, the thing that is happening here is that you have a space, it has been reduced to half of its size, and in a sense, there's two types of strings, the strings that are free to move on this side, and they have mirror images here, and there's strings that are sort of stuck at the orbifold plane. And so it's, I don't know, it's a little unclear what we do, but the procedure is very clear in string theory. It's a successful procedure. The procedure is take the original theory, let it be invariant under the symmetries that create the orbifold. Then take new possible closed strings that could appear that are closed by virtue of the symmetry. So they're exploiting really the intrinsic structure of the space, and this gives you a whole new set of states. So you lose some and you gain some, basically is the philosophy here. So let's do superstrings. Let's begin this. So what is it with superstrings? Superstrings are needed because they contain space-time fermions, which are necessary in any theory that is hoping to describe nature. So what did we have in our bosonic string? We had x mu's of tau and sigma that were classically commuting. In the classical theory, these were commuting variables, but in the quantum theory, sometimes they're commutators, and they are different from zero, some commutators. Well, to do fermions, we're going to introduce things on the world sheet, new kind of fields. So you could say, are you going to write a Nambu-Goto action and add the fermions? We could try to do it this way, but it's very complicated. We'll write a different kind of action. So we'll have an action that will be Nambu-Goto, if you say, for the x's, but a new action for the psi's. The psi's are going to be psi's of tau and sigma. They also live on the world sheet. The x's had the interpretation that they are the embedding of the string into a normal space. People try to think of the psi's as embedding of the string, map of the string into some superspace of anti-commuting coordinates. Now, this will be a classically anti-commuting variable. So actually, classically, the anti-commutators would be zero. So any sort of anti-commuting object, you have two of them, B1 and B2, and they're classically anti-commuting, then it's equal to minus B2, B1, which is to say the anti-commutator is zero. But sometimes, if you have interesting things, the anti-commutator can fail to be zero, and that's in the quantum case. This is quantum. An anti-commuting variable also satisfies this among itself. So B1, B1 is equal to minus B1, B1 if you reverse order. Since it's equal to minus itself, is zero. So what fields are we going to need? Actually, you're going to need what is called a Dirac fermion on the two-dimensional world. This is a scalar on the two-dimensional world. Doesn't have indices with tau and sigma. This index is accidental. This thing will sort of have a mu again, but that's accidental. But in a sense, there's an index here that takes two values, an alpha index. So this thing is a single unit, and it has a psi1, a psi2, two of them that they comprise together a nice unit in the two-dimensional world for a fermion. So if we're going to do our thing in the LightCon, as we're going to do, there's going to be LightCon gauge conditions, which x plus, and there will be psi pluses also. The x plus is equal to proportional to p plus tau. The psi pluses will also take some, I'm sorry, there's a mu here as well. So all the calculations we've done are going to change a bit. They're going to be similar, but they're going to change a bit. These are acted by a Lorentz transformation. These are acted by a Lorentz transformation. And these are acted by a Lorentz transformation. So actually, these are all vectors under the Lorentz group, which should say to you, wow, if fermions come out of here, it's a real miracle, because this seemed to come from vector representations of the Lorentz group. And fermions are supposed to be spinor representations of the Lorentz group. So where in the world are the fermions going to come? This thing may be something like a fermion in 2 dimensions, but with an index like that, how is it ever going to give you a fermion? Well, it's very interesting how it will happen. It will be a very subtle thing, but it will happen. And it's so interesting that it happens that, in a sense, the person that was playing with this most seriously, who was Ramond, discovered supersymmetry in 2 dimensions by looking at this thing, something we're going to see. Not today, but tomorrow. Hard to believe you're going to get fermions with something that in space-time has a vector index, but we'll see how it happens. All right, so time to write an action for these things. So here it is. We're going to have LightCon variables. Yes. What's funny? Oh, why there are just 2? Yeah, well, that's the minimal situation, basically, that you can get in 2 dimensions. It's the size of a spinor in 4 dimensions. The Dirac spinor has 4 complex components. In 2 dimensions, you can get by with less. In a sense, what is going to happen is that one of them is going to be waves moving in one direction, one is going to be waves moving in the other direction, is the least you need to generate something consistent. So here's our action. S of psi is 1 over 2 pi. And this is a fermion action written in a funny way, but psi 1 I dd tau plus dd sigma, psi 1 I plus psi 2 I dd tau minus dd sigma, psi 2 I. You can worry about something pretty strange about this. It's a worry that it's always there in a fermion theory, but here is very obvious. Suppose I tell you, look, here is psi 1I dd tau psi 1I. Why isn't this a total derivative? Well, it is not a total derivative, because if it would be a total derivative, it would have to be like dd tau of a psi 1I psi 1I, maybe with a 1/2, but this is 0. So this is not a total derivative, only because these variables are anti-commuting. That's why you don't have actions for scalar fields that look like this. But if they're anti-commuting, this is 0. You evade the possibility that this is a total derivative. So this is a meaningful action. The dd sigma would be the same question. Why isn't it a total derivative? It's not. So let's do the equation of motion, the variation of this thing. So equation of motion. So let's vary just this field. Vary this. And the other one is similar to vary. So a couple of things we can notice. We're going to have to vary this one, and then we're going to have to vary this one. This one is standard. You vary this. But when you vary this, you have to integrate by parts. And you're going to get a minus sign when you integrate by parts. And then you're going to move the variation to the left so that it looks in the same position here. And that minus sign is going to cancel. At the end of the day, when you vary this psi 1 and this psi 1, you get twice what you get when you vary just this one. So this is always happens for Fermi's. If the signs would be badly thought out, the variation of this would cancel the variation of that and would get 0. But happily, these are anti-commuting, so it doesn't happen. So the variation of this thing, delta S of psi, you'll get 1 over pi integral d tau, the 2 cancels, so it's d sigma, delta psi 1I, d tau plus d sigma, psi 1I, and you get the dd tau total derivatives we always ignore, but the dd sigma is going to be important. So in here we're going to get plus, this term, plus 1 over 2 pi integral d tau, and the sigma goes away. So psi 1I delta psi 1I between pi and 0. Let's go, this is backboard. And this is middle. Ooh. So, if I do both of the fermions at the same time, we're going to get the following. The total delta S is going to be 1 over pi. I did just the first fermion. Let's do the second fermion. 0 to pi. You get delta psi 1I d tau plus d sigma of psi 1I plus delta psi 2I d tau minus d sigma psi 2I. You would imagine that gives you that, plus 1 over 2 pi integral d tau of these things, psi 1I delta psi 1I minus psi 2I delta psi 2I between pi and 0. Okay. Okay, so what are the equations of motion? Equations of motion are d tau plus d sigma psi 1I equals 0, and d tau minus d sigma psi 2I equals 0. And the sigma, of course, goes from 0 to pi. We're doing open strings. Okay, how do you solve this? That's sort of easy to solve. Psi1I of tau and sigma is some sort of chi I1 of tau minus sigma. It's a wave that moves to the right. This solves the first equation. And the second equation, psi2I of tau and sigma, is some sort of wave that moves to the left. Pretty nice. Waves that move one way or another. How about boundary conditions? This is where it gets strange. Psi1I tau sigma star delta psi1I tau sigma star minus psi2I tau sigma star delta psi2I tau sigma star must be 0. Okay. Well, let's use our bosonic intuition. That should help. We had similar things for the open string, for the first coordinate, for the second coordinate. We treated them all independently. So let's make this variation go to 0, and this variation goes to 0. Pretty reasonable. So let's say I have this. This psi1 could be fixed, or psi1 could be 0. Well, psi1I of tau, say sigma equals 0, equals 0. Okay, that looks like a nice boundary condition for a fermion. Let's see what it means. I go back to the solution. The solution says psi1I of tau 0 is therefore equal to chi 1I of tau, and that's 0. So chi I is 0 for all values of its argument, because tau runs over all values. So chi I is of u or v is 0. So this is 0, and the fermion is 0. So you make the fermion 0 at one point, you make it 0 everywhere. Not good. Similar is with this thing, if you try to make this 0. So we're in trouble. But, so, you have good explanations, and I convince you in the case of the bosonic string that, yeah, the ones and the different coordinates shouldn't be mixed. They're independent. Maybe they're not. And our only hope is to cancel these ones with these ones, actually. And now you could say, okay, let's try to say it in a different way. Actually, this is not so bad, because yes, the x's, x mu's, all the x's are independent. They represent the propagation of the string in the world. But the two psi's come together. They're part of a Dirac fermion. So they're not that different from each other. So relating them need not be so bad. Now, you could have related things even with the x's, and that meant that you put some strange boundary condition or something, and you didn't need to or didn't have a physical application. But here we will need to, and we will have a physical application for this. So the only way we can do something that doesn't make the fermion zeros is relate psi1 and psi2. So let's try relating the two fermions. And we're almost done for today. Let's say that we put that psi1I of tau and sigma star is equal to plus or minus maybe two choices of psi2I of tau and sigma star. Well, if these two fermions are the same at sigma star, they should always be the same, so their variations should still be the same at sigma star. And now when you multiply this, you get psi1 delta psi1 of tau and sigma star. The plus and minus go with each other, so you get plus delta psi2 delta psi2 of tau sigma star. So a plus, so this thing works, this gives 0, and this is a good way to put boundary conditions. So this is what we have to understand. Now, there seem to be a lot of boundary conditions here, but there are not that many, and we'll finish with that. It's going to take 3 more minutes. Apologize, but we really want to see that coming to an end. So what do we have here? This is the front blackboard. Okay. I want to make another remark here, that this fermion action that we've written is invariant if you change psi1 by minus psi1 or psi2 by minus psi2. So a little bit of these signs are irrelevant. So we can do that. We can suppose this would be equal to that one or minus equal to that one at sigma equals 0. Suppose it's 2 possibilities. It could be equal to the second fermion or different from the second fermion at sigma equals 0. So we use that freedom that the fermion really is only defined up to a sign once and for all, and we declare that psi1 of tau 0 is equal to psi2 of tau 0. Always. And then the second point, psi1 of tau pi, could be plus minus psi2 of tau, this is 0, pi. So these are our boundary conditions, and the plus, there's the plus and the minus. I'll put them separately, plus and minus psi2 of tau pi. The plus is going to lead to something that is periodic, and is going to lead to the so-called Ramond sector. And the minus is going to go to the Neve-Schwarz, no T, sector. So let me do one more little thing here. This is what everybody does, and in a sense, this is a trick we do also for open strings. Remember, we did with open string, we had x dot plus minus x prime, and we didn't go through the whole sort of technical details of how do we derive the oscillator expansion. But if we did, you would have seen that what one usually does is create you have a field that goes from 0 to pi. All your coordinates are defined. Sigma goes from 0 to pi. So everything is defined here. But somehow you want to create something that goes from minus pi to pi so you can use applied periodicity conditions in the usual way. So what we're going to do is the following. We're going to define a new fermion, psi capital I, that is going to be psi1 of tau and sigma here, and psi2 of tau minus sigma here. How does that make sense? Well, psi1 and psi2 just live from sigma equals 0 to pi. So here is this new field is psi1 from here to here. Now, psi2 also lives from 0 to pi. So when sigma is minus pi over 2, well, you get the field psi2 at tau plus pi over 2. So in this region where sigma is negative, psi2 minus sigma is positive, and therefore this is well defined. So this is we can say that psi I of tau and sigma, the new field, that lives from sigma from 0 to 2 pi, is going to be psi 1I of tau sigma for sigma in 0 to pi. And it's going to be psi 2I of tau minus sigma for sigma between minus pi and 0. And look at this, where we had here psi 1 of tau and sigma is a function of tau minus sigma. But psi 2 of tau minus sigma is also a function of tau minus sigma. So this whole field you've defined here is some function, new function, of tau minus sigma. Moreover, this whole field is continuous here because of this condition. Psi 2 at 0 and psi 1 at 0 is here. But psi 1 at pi is going to be either minus or plus psi 2 of pi. So this field, this whole field, psi I, say, of tau pi is going to be psi 1 of tau pi, which is plus minus psi 2 of tau pi, which is plus minus psi of tau minus pi. So this plus minus sign that we had here in the possible boundary conditions means that this composite fermion that runs from minus pi to pi, that is continuous here, is either periodic or anti-periodic. So at the end of the day, we get from here, and now it's the last line I'm going to write, but it's the end of the story and sets up well for tomorrow, that psi I of tau pi, this field that lives from minus pi to pi, is equal to psi I of tau minus pi, gives you the Ramond sector. And if it's equal to, well, I'll write it again, psi I of tau pi equal to minus psi I of tau minus pi, is the Navier-Schwarz sector. Please review this for tomorrow. Make sure you understand it because it's going to take on from this. A curious fact. Most of us believe that periodic things are easier than anti-periodic things. So most of us would tend to believe naively that the Ramond sector is simpler than the Navier-Schwarz sector. Totally wrong. The anti-periodic sector is sort of easy, and the Ramond sector is very non-trivial. And the periodic fermion is really a very interesting object. So we'll see you tomorrow.